study sums of independent identically distributed random variables in this video. Now let us try to define the independent and identically distributed, popularly known as IID of random variables. It's a collection of random variables which has the same probability distribution, but all of them are mutually independent. Let us define W, that is equal to summation of I value varying from 1 to n xi, where expectation of xi is equal to expectation of x, that is equal to mean of x, mu x. Variance of xi is equal to variance of x, that is equal to sigma x square. Expectation of xi xj is equal to expectation of xi square, that is equal to expectation of x square, the sum of mu x square plus sigma x square for j value x equal to I. If j value is not equal to I, then we can write this expectation of xi multiplied by expectation of xi is equal to mu x square. When n value is equal to 2, W2 can be defined as x1 plus x2, that is expectation of W2 is equal to 2 times mu x, and variance of W2 is equal to 2 times sigma x square. When n equal to 3, W3 is equal to x1 plus x2 plus x3, expectation of W3 is equal to 3 times mu x, and variance of W3 is equal to 3 times sigma x square. In general, we can write this as Wn is equal to Wn minus 1 plus x of xn. So expectation of Wn is equal to n mu x, and variance of Wn is equal to n sigma x square. The characteristic function phi w of j omega is equal to phi x of j omega to the power n. Let us study now about law of large numbers. As you see that we have seen in the previous slide that the mean increases with the value of n, and you have seen that the mean value becomes multiplied by n mu x, and even the standard deviation square also gets multiplied by n. If the value of n is very large, then we can see that mean and variance also get very large in proportion to n. Therefore, in order to maintain a reasonable small value, we should go for averaging. So therefore, let us introduce a new random variable y, that is equal to 1 over n summation I value varies from 1 to n xi, where y is the average of xi, which are assumed to be independent identically distributed random variables. Y can also be written as y is equal to summation I value varying from 1 to n xi by n, by multiplying each term in the sum by a factor of n. So when we take the expectation of xi by n is equal to expectation of x by n, that is equal to mu x by n. Variance of xi by n is equal to variance of x by n, that is equal to sigma x square divided by n square. Therefore, we can say that mean of y is equal to n times mu x by n, that is equal to mu x, and the standard deviation whole square is equal to n times sigma x square by n square, that is equal to sigma x square by n. So, following important observations are made. The mean of y is same as the mean of x. The variance of y decreases by a factor 1 by n, and with the central limit theorem, which we will be studying later, y tends to be Gaussian with the given mean and variance. Let us now define central limit theorem, which is also known as sample distribution of mean. Central limit theorem says that under the condition that random variable x has a finite mean and finite variance, as n becomes arbitrarily large, the PDF for the sum W approaches the Gaussian PDF itself. Let us consider x1, x2 up to xn as the random variables with the expected value mean P of xi is equal to mu x, which is less than infinity, and variance of the VA over of xi is equal to sigma x squared less than infinity. Then the random variable Zn can be defined as x bar minus mu x divided by sigma x by root n, where x bar is given by x1 plus x2 up to xn divided by n minus mu x divided by sigma x by root n. That is equal to x1 plus x2 up to xn minus n into mu x divided by root n sigma x. The standard random variable converges as n goes to infinity, that is limit n tending to infinity, probability of Zn less than or equal to x is equal to phi of x, that is equal to standard normal PDF. The essential component of the central limit theorem is that the average of the sample mean will be the population mean. The average of all of the standard deviations in the sample, we will find the actual standard deviation for the population. Example, let us consider a case where xi are uniformly distributed between 0, 1. If the random variables are IID, then we know that mu x is equal to a plus b by 2, 0 plus 1 divided by 2, that is half. Sigma x square is given by b minus a whole square divided by 12, so 1 by 12. So Zn is defined as x1 plus x2 up to xn minus n into mu x divided by root n sigma x. So that can be written as x1 plus x2 up to xn minus n into mu x is half divided by root n, root of 1 by 12. When n equal to 1, z1 is equal to x1 minus half divided by root of 1 by 12, and the PDF for z1 is given as shown here, which is almost a rectangular wave. z2 is given by x1, n value is 2, so x1 plus x2 minus half into 2, that is 1, divided by root of 2 by 12. And the PDF for Z2 is almost a triangular wave as shown in the figure. When n value is equal to 3, Z3 is equal to x1 plus x2 plus x3 minus 3 by 2 divided by root of 3 by 12. And the PDF for Z3 is shown here. Z30, when the value of n goes very large, n value is equal to 30, it is summation of I value varying from 1 to 30 xi minus 30 by 2 divided by root of 30 by 12. The PDF for Z30 looks like a Gaussian curve. Zx is the normalized sum of independent uniform 0 to 1 random variables, which we have defined in the previous slide. And you can observe that the shape of its PDF from triangular as n value increases, it looks like a normal curve, Gaussian curve. So that is what the central theorem says. As value of n increases, the PDF becomes a Gaussian PDF. Let us consider one application. In a communication system, each data packet consists of 1000 bits. Due to the noise, each bit may be received in error with the probability of 0.1. It is assumed 6 errors occur independently. Find the probability that there are more than 120 errors in a certain data packet. assume Bernoulli distribution. So given here, you can understand here the mean probability is given 0.1. Sigma x square it can be computed here with 0.1 into 1 minus 0.1, that gives you 0.09. The probability of y value greater than 120 errors is given by Bernoulli distribution we are considering y minus n mu x divided by root n sigma x. That is, y is 120 here, n value is 1000 multiplied by mu x value is 0.1 divided by root n, that is 1000, and sigma x square we have got it as 0.09, so therefore it is root of 0.09. So that gives you 2.1082. Therefore, it is 1 minus pi of 2.1082, and that is almost equal to 1 minus, it is from the table we have got it as 0.925, so 1 minus 0.9825, that is equal to 0.0175. Thank you. In the next video, let us study on conditional joint probability.